All right, people, I'll just begin with the code. So the first thing we do, as always, is import the libraries. Now, many of these libraries you have not used yet, but they don't have a very big role here. So you won't need to know the exact working of how this did do things. I've already written out in comments what each library does, but I'll just go through it once very quickly. Now, CV2 is an very important library. It is used for image processing. Now, why do we need image processing in audio classification? It's because I told you we're going to use ResNet, right? So what ResNet is built for is image classification, basically. Now, how will we do image classification if we have audios? So what we are going to do is we will convert them, all the audios, to MEL spectrograms. Okay, and then that will be fed to ResNet, and then we'll get the classification we need. Okay, so that is what we are going to do in this code. So this is what CV2 is for, to manipulate those images, the smell spectrograms that we're going to get. Audio read, as the name suggests, logging. Okay, so this is important when you want to debug and monitor your activities. Okay, so what it does is it logs everything. Okay, the every run of the code, it will be logged here. Okay, so the moment it stops working, your code stops working, you can go to the log and you can find the exact place, exact line of code where it stopped working. And then you can debug it. Okay, and as for monitoring, we'll see this later. Okay, how it will help us monitor what is happening with our code. Okay, where the code is running. Previously, we run many epochs, right? So we had an idea of which epoch was running when. So that is how we can monitor where our code is right now. OS we have done. Random is just to shuffle the data. It randomizes things. Time is to calculate how much time things are taking. Warnings is just tells us how what potential issues our code might have. Librosa we have done. NumPy, Pandas. Sound file is just for reading and writing audio files. Then we have Torch, PyTorch, which is the base module of PyTorch. Then we have the neural network module, and then the functional is for element-wise operations. Okay, in the neural network we have a lot of elements, and if we want to perform a certain operation on each and every one of them, we use this. Okay, and the next utils.data is just for loading your data during training. Okay. Then context manager here is just to oversee key things are running smoothly. Okay, that's all. Then paths is just to treat your paths in a more object oriented way. You've studied coding, so you know that there's a concept of oops, right? So that is what paths is there for. Now, optional is just to specify the type of data that can go into your code. Okay, so for example, you have specified, say, addition operator. Okay, so now you want to only add string values, right? You want to concatenate them. So you can just uh, give the hint to your code. Okay, if it is a string value, then only add them. If it is an integer value, do not add them. Okay. Then we have the progress bar, as the name suggests. And then we have F1 score. This is the metric we will be using. We need to maximize the F1 score. I'll send you a link to evaluation metrics if I haven't already. So that is what will happen. And then we have models, which actually contains our pre-trained ResNet model because we are not training it from scratch. It already exists. So that is what we are going to use. Okay, so here what we do is we set a seed. Okay, so it's basically exactly like we did random state, right? We set a random state number. So every time we run that, we get the same training values and the same testing data, right? So that is exactly what this is. So we set the seed for all of these things. Okay, for the random, we imported random, right? So we set it for that. We also set it for numpy.random, for this hash seed. Okay, hash is basically a hash table, and that here that just means a dictionary. Okay, a dictionary as in it contains key value pairs, like 1 goes to A, 2 goes to B. So if you want to call B, so you call dictionary and you call the number 2. So 2 is the key that refers to the alphabet B. Okay, so that will be called. So we are using a lot of dictionaries here. So we need them to have the same key value pairs each time. So this is why we use hash. Okay, and then we have manual seed. This one is for this, like we have a random for NumPy. So this is the same thing for PyTorch. And then the same thing for CUDA. CUDA is just so um, we do the operations on the GPU. Okay, this will run on the CPU and CUDA runs on the GPU if you have one. If you do not have a GPU in your computer, then it will automatically go to CPU. This will not create a problem. Okay, and then there is the CUDA deep neural network. Uh, Here we set it to the deterministic mode. Okay, don't worry about what that means for now. And then to improve the performance, we also set benchmark to true. Okay, all of these are just setting seeds. And then we create a logger. Okay, since we need to log all our activities, we do that here. First, we get the logger. This is a function. For example, it's basically the same thing like you did in label encoder, right? You did the variable le is equal to label encoder and these brackets, right? So it's basically the same thing. You get that logger in this variable logger, and then you define a formatter as well. What is the format you need your login? So you need the time, you need the level name. There are a lot of different kinds of information you have when you log things. Okay, a lot of things are happening. So which level is that particular action upon? So that is the level. And then you have the message. Okay, exactly what is happening. That is what I've written here. It's the timestamp, log level, and the message. Now we have handlers. Okay, handlers are objects that transfer that log from some place to some other place. Okay, um, we'll see this as well. And we set the level to info. Okay, so we only need to capture the log that is on the level info. Other than that, we do not need it for now. And info will basically log everything you actually need here. Okay, it does not go too deep into the code. Okay, so I told you that handlers basically send the data to some place. So we define a handler, which is a stream handler. So this will um, take your data and it will get it to the console. Okay, basically this area where you need to print it. And you set the format for it. The level is info. And to this logger, you add this handler. Okay, so you add that. So your logger is built basically. Now, if out file is not none, which means if you have specified a file where you need to log everything, okay, you can do that as well. If you specify a file, then all your loggings will be saved to this file. Okay, same format, same level, and you add the handler. Okay, and then this will be the first thing you see, logger setup. Okay, as soon as you enter the data, logger will be set up. And then from this function, you get the logger in return. Okay. And then you have the context manager. This is this @ is called a decorator. Okay. After don't worry about what that means because it's basically a feature of Python. Okay, decorator. So here it is only used to measure the execution time. Okay, so for the timer, we have set a name. It has a specified name of what exactly is the thing we need to find the time of. And you can add a logger there. This is optional. You don't have to have it. And initially its value is set to none. Okay, now this function gets the current time in T0. Okay. And then this is what the message says. I'll run this. Okay, so this is a message that this thing has started. Now, if your logger is none, then this is the message you will see. Okay, and otherwise, you will get the info message. Okay, so it's basically just that. Okay, and then you set a target value for your this SR. You extracted two things from your data, audio data, right? It was Y and it was sample rate SR. So you set the target sample rate. Now you do this because see, I told you, na, Librosa has a specified sample rate that it samples everything to. So if you want to have a different sample rate, you're going to have to specify it. Okay. Okay, and then we have the test CSV data. We have the test audio data. We print the head, and this is what it looks like. Now, see, the point here is if, see, when I gave you the data set, you need to read. Okay, you need to read everything about that data that is already given there. Okay, so there it specifies that for site 1 and 2, the recordings have been labeled at every 5 seconds. Okay, this is the test data, so you won't see a label, but actually they have been labeled at every 5 seconds. Okay, now if they have that same label, then obviously they are the same bird. Or if they have the maximum number of same labels for a particular audio. Okay, so you'll see that after 5 seconds, 10, 15, 20, 25, it's for the same audio only. Okay, these are the seconds. Now for site 3, since labeling them for every 5 seconds was very difficult to do manually. So what they did was they only did it for site 1 and 2. And for site 3, we have a huge data, say 10-minute data, 10-minute audio, and we only have one label for it. Okay, so that is the values we have for training. Okay. Now we define the model. So we have created a class called RESTNet, and it carries the base class of PyTorch. Okay, so we are extracting it from here. Now we define a constructor. In any, if you define something like this inside a class, it is not called a function anymore. This is a constructor method. Okay, and this has the parameter self because if self is not there, you won't be able to modify it. Okay, so since you need to modify it, it needs to have this self parameter here. And then we have the base model name as a parameter. We'll need to have that. Initially, pre-trained is set to false, which means when we have our model, say ResNet in this case, it will have some pre-trained weights. Okay, you know how neural networks work, right? So they have a certain weight associated with them. Okay, so here we have set those pre-trained weights to false initially. Okay, and the number of classes is 264 because that is the number of different birds we have. Okay, if you print the eBird code wale column ka unique values, you'll find them to be 264. Okay, now we initialize this ResNet. Okay, the super is basically the super class of this constructor, which is ResNet. So we initialize that. And then for the base model, we get some attributes from this particular model, which we need to specify when we call this function. It's a parameter we will give when we call this. So here we will later give ResNet 50 as the base model name. Okay, so we'll get that. And for pre-trained value, we will get this. Okay, whichever here is specified. If nothing is there, then it will automatically take it as false. And then we create the layers. Okay, so since the ResNet model is already there, so we take all the layers of it except the last two. Okay, we don't take those layers, and generally they are pooling layers and dense layers. Dense layers are fully connected layers. Okay, and pooling layers are basically used to reduce the dimensions. Okay, since we use a lot of neurons, so at the end we need to reduce those dimensions, right? So here we add a pooling layer. Okay, it's an adaptive max pooling layer. So we add it. What this one means is that say you have three directions for it, x, y, z. What it will do is if your model is in xy direction and extended to the z direction, what it will do is that it will set that z direction to 1. Okay, which means that you will basically not have a z value. You'll only have the xy values. Okay, it will just say squeeze it. Okay, and then you'll find a 2D layer. Now you define an encoder. This encoder will be a sequential model. Okay, we have already done this. And all the layers it will have are these. Okay, the base model except these last two layers and one adaptive max pooling layer. Okay, so this is our encoder. Now for input features for the fully connected layer, we'll extract the input features from the fully connected layer because the fully connected layer will have each and every feature. Okay, each neuron will specify one particular feature. So that is what we'll take from there. And then we define a classifier, again, a sequential model, and linearly it will operate and it will have the input of these number of input features and it will give an output of 1024. It will be ReLU and we have a point to drop out. Again, this is the input here and the output is here. And the last layer, our output should be the number of classes. Okay, because we'll ultimately find the probability of that particular audio belonging to a particular class. Okay, so next we define another method. Here, the input tensor will be given. Now we'll extract the batch size from that tensor, and then we'll apply this encoder to this, and it will convert it into a 1D tensor. This will send to the classifier, and then uh, after that is done, we will do softmax. See, F is here because we need to do an element wise operation. Okay, we need to apply softmax to every element. So F is here. We imported it earlier. So first we'll do softmax for one thing and another will also do sigmoid. Okay, we are doing two activation functions for two different variables. Okay, so we'll have two different probabilities. Okay, so the logits is basically our input X, and there are probabilities for by using the softmax layer and one for sigmoid activation function. Okay, so that is what we get from this particular ResNet model. Now we need to specify some parameters. There is model configuration. The base model name is ResNet 50, which we are going to use. Pre-trained is false, so we are going to train it. And then the number of classes is 264, as we know. Now for the MEL spectrogram that we're going to create, the number of MEL pins is 128. The minimum frequency is 20 and maximum is 1600. Now I need to see this in all of your EDAs. Sorry, in your FEs. Okay, you need to find for all audios you have, you need to find the minimum and the maximum frequency. Like I know there are a lot of audios, so you cannot do it for all of them, but try to do it for the maximum of them. Okay, like get an idea of what the range is. So you can specify these two values on your own. Now there is this weights path. This is basically, it basically has pre-trained weights. Okay. For this particular ResNet, it has some pre-trained weights. So we add those weights here in weight paths. Okay. And now this is exactly what you have done before. You have a lot of eBird codes, right? There are 264 of them. So what you do is you label encode them. Okay, for in your train CSV file, you label and code them. And if you print this, see, you'll have these values for all of your 264 uh, eBird names. Okay. And then we have an inverse. Okay. Because you need it, because you will feed this 0, 1, 2 values in your model. But after you get the prediction, you need to convert it back to the name of the bird, right? So this, what this does is it takes this key and makes it the value, and it takes the value and makes it the key. Okay, so if you call 0, then you will get all fly. If you call 6, you will get impip. Okay, so if you print that, see, 0 all fly and 6 is impip. Okay, so that is what you'll get. Okay, now this is important because when you create the MEL spectrogram here, you will get values in one channel. Okay, and ResNet-like models are basically built for 3 channels, RGB values. Okay, because it is made for image classification, and generally you don't really get like black and white images or something. You don't get mono images, you get RGB values for images. Okay, so what we need to do is we need to convert it into RGB values. The MEL spectrogram we have, we need to convert it. So we get an array for that spectrogram as the parameter here. We can specify the mean, standard deviation, the maximum value for normalization, and the minimum as well. And we define a variable called epsilon, which has a very, very small value. We'll see why this is here. So we'll stack those in, we'll stack this numpy array in thrice for R, G, and B, and the axis will be -1, which means the last axis. So if your this X is in XY direction, so when you do X -1, it will be stacked in the Z direction. Okay, that is the right way to do that. So this will happen. You find the mean. If it is already specified, then that. And if not, then you'll find the mean, and that will be your mean. Subtract it, find the standard deviation the same way, divide by standard deviation. Now this plus epsilon, this thing comes here because it is possible that your standard deviation might be 0. And then you'll get an error because division by 0 is not possible. So what you do is you add a very, very small value here, so it does not give you an error. Okay, and then you find the minimum and maximum of standard deviation of this new thing you have created, new array. You find the maximum and minimum for normalization. If it is already specified, then it will be that. And if not, it will take these two values. Okay, now if the range, max minus min is the range, if it is greater than epsilon, which means it is a somewhat substantial value, then you create another array where if the value for any element is less than the minimum normalization value, then you'll set it to the minimum value. Okay, if it is less than that, then it is equal to this. And if it is more than the maximum value, then this. And then you convert it into 0 to 255 values. Okay, RGB values. And then you convert them to, this is basically int data type. Okay, so you do that because RGB values are never like 244.75. It is always either 244 or 245. Okay, and if it is not not greater than this, which means it is equal to or less than the epsilon value, which means it is not a very substantial value, then this is everything we put to 0. Okay, and then we return this array, RGB values. Then we have our test data. Okay, here we give a data frame. The clip image size is 224. This is the default value. Okay, it's 244 into 541 basically. Okay, so that is the value of the MEL spectrogram, the size of the MEL spectrogram that we are going to get. Now we have MEL spectrogram parameters that we've already specified above. Now you do the self thing, so you can modify all of these. Then you find the number of samples. From the DF, the raw, you find all the number of rows there, which means the number of samples we have. and then you get an item from there. The sample rate is already specified above, so you can write sample rate here. And then you return that particular raw. Okay, this is an index that is specified. So for this index, you locate that raw and you extract the site number 123 from there and the row ID. Okay, so if the site is 3, then what you'll do is this is basically it starts with 0 and it ends at 5 seconds. Okay, because the what I told you that the site 3 is a very long clip. Okay, it might be possible that is a very long clip. So we don't exactly know how long they are. So what we do is, just like sites 1 and 2, we split them into we split them into um, batches of 5 seconds. Okay, so this is exactly what is happening here. So we do that. Okay, and then we create the MEL spectrogram. We find these values. We give it the parameters, and then we convert it into decibels as we did earlier. Then we create the convert it to color. We extract the height and width. We resize it based on the compatibility with our model. So we do that. And CV2 is only used here. I don't think it's used anywhere else. And then we move the axis. Now, here, what we have is it's the color channel comes later. Okay, it comes at the end. So what we are doing again, it's all to make it compatible with the model we have. If you do not do this, then you'll get an error that it's not compatible or something. Okay, so you'll get an error. So this is important. And then you normalize the values because all the values are from 0 to 255. So you divide it by that and you get some value. Okay. And to an images list, this is a list. So you append that image value, that array values, whatever you had. And okay, so you set it as an array and you return that array. Okay, so you get that. Now this was for site 3. Now for site 1 and 2, we already have those clips are basically clipped at 5 seconds, right? So what we do is we start at the end and we subtract 5 seconds from it. For example, if the clip was say 5 seconds and 20 milliseconds, so so basically the start seconds will be 20 milliseconds and the end seconds will be 520. Okay. So we do that, and this is everything is similar here because we need to extract the same thing. So this is similar, except we don't need to append anything here because here what we did was we, for the same clip, we had a lot of values. Okay. We extracted values at every 5 seconds. So we had to append it all. Here we only have one, so we don't need to append anything here. Okay. Okay, now for the prediction loop, what we have is we get the model. Okay, there is a configuration dictionary and there is weight paths that we already specified. We also specified model configurations above. Now the model is ResNet and we have the configurations. We specify the checkpoint and we give it the pre-trained weights. We load it and okay, so we load it and we initialize these parameters. Okay, and then our device is GPU. And if this is not available, it will automatically go to CPU. Okay, so we send that model to our device, CPU or GPU. We put it in evaluation mode and we return the model. Okay, and then for the prediction clip, again, we for every clip, we have this, we pass a data frame, we have a clip, we have a model, MEL spectrogram, and the threshold. So anything above this will be considered positive. Okay, if for certain labels, if you have the value above 0.5, then it will be considered positive, otherwise not. So we have our test data set, same thing. We load the data and our device is, again, it's GPU if it is available, otherwise it's CPU. evaluate it, and then we create a dictionary for the predictions. Okay. And then we extract this from each value. We extract the site and row ID like we did before. And if it is in site 1 or 2, then you send that image device. You don't need a gradient here. The gradient is only needed if you're training your model. But here we are trying to predict something, so we don't need gradient. So we set that, and then you predict something with your model. You find the probabilities, and then see if it is greater than the threshold, then this will be true, right? So if it is true, you add it to this labels list. Okay. And if it is not 1 or 2, so site is not 1 or 2, what you do is you set the batch size. Okay, so because our clip might be very long, so it'll run for a long time. So what we do is we create batches of size 16, and on those batches, we apply the entire thing like we did above. We create a set for all events. Okay. The difference between a set and a list is that list can have repeated values and set cannot have that. Okay. So we do that. And again, this is exactly the same thing that we did above. All of this is the same. Okay. And right. In the data set we had, it was given that it might be possible that the data does not have a bird call. So if the label length is 0, which means none of them is matching, then we predict it as no call. Okay. Otherwise, we create a list and we join the things inside that list. So it will have the predictions for every 5 seconds. Okay. Of that particular data, particular audio you have, and it will return your dictionary, okay, that has the site and your audio clip and then the label. Now you define the prediction similarly. You have, because this is basically what we'll be using. This is prediction per clip. Okay, but we need the prediction for the entire data. So again, we'll pass these parameters here. We'll get our model. We'll have unique audio IDs. If you look at the CSV file closely, then we have this particular column where the IDs are similar, but the audio clip name is different. Okay, I think it's here. See, audio ID is the same, but row ID is different. Okay, but it's basically the same clip, just in different seconds. Okay, so we need to predict one for each, right? One for each audio. Okay, so we ignore the warnings. We create again a list. And here what we do is we start our timer. Okay, we start our timer for when the prediction is starting. Mono is true. We did rest type before as well, case of past. And then for the test audio, we'll extract a particular audio. Okay, for one audio ID, we'll extract that and we'll drop that raw because we have already extracted it, and we'll reset the index so it does not harm our data frame. And then we'll predict the value for this particular audio ID. Okay, so we do that and we create a dictionary. Okay, so this is there. It has this dictionary is basically this one. Okay, the one we get from prediction for clip. Okay, so prediction for clip is done, and we give it the parameters that are needed. Now, okay, so for the dictionary, we create we have this raw ID as our key, and then our particular prediction as the value. Okay, dictionary have key value pairs, right? So we add the key values to raw ID and the values to bird. And then we create a data frame with those two. And we append all of these values to to the list. And from that list, we add everything there. Okay, so we have our final prediction for all our values. For the submission, we do the prediction, we give it all the values we need. Our threshold here we have specified as 0.8. And if you want, you can play around with this. And this creates a particular submission CSV file. Okay. And index is false. If you want to do index is true, then that will happen is you'll have this another column called index, and it will have this same 0, 1, 2, 3 values. Okay. So since they're already there, we set them to false. And when you run this, you can see this is what log does. If you did not have a logger, you won't be able to see this. And it gives you all the time since you specified that you need the time. It starts when the prediction is starting. And then it will tell you, okay, the prediction was done in this amount of time. And you have the progress bar because you imported them and you added those. Okay, and then if you print the submission, this is this is the CSV file you have. Now what you need to do here is if the um if the row IDs are basically equal, okay, and they have this 5, 10, 15 differently, then you need to find the mod of these values you have, and then you'll create a particular row ID which is only up to this point. Okay. And then you'll give it a label of whatever bird it is. Okay. So that is something you will need to do. You can also plot those F1 scores, and your model will be evaluated based on the accuracy of this submission. Okay. It does not have a lot of values. I think there are only 15 audios here, but you will be evaluated on their accuracy. Okay, so that is basically what you need to do. And okay, so I think that's it.